Good morning, everyone. On behalf of Dr. Rohit Mehra, sir, Professor at Dr. B.R. Ambedkar National Institute of Technology, and Professor Shinji Tokonami, sir, our esteemed foreign coordinator, I extend a warm welcome to all participants on the third day of the GIAN course. Without further delay, I now invite Professor Shinji Tokonami, sir, to commence the first lecture of today's session on the dosimetry of radon isotopes.
May I start?
Sir.
Okay.
Sir, please share your entire screen rather than sharing a window.
Okay. Wait a moment. Can you see my slide?
Yes, sir, it's visible, sir. Yes, sir.
Okay. Okay, thank you. Okay. Hello, everyone. I'd like to start today's lecture, but yesterday in my yesterday lecture, it was not enough to explain this table. This is very important, and we can understand the historical history of ICRP publications in terms of those conversion factors. So I'd like to repeat again. So 1987, from the dosimetric approach, ICRP gave us two different dose conversion factors, indoors and outdoors. From publication 50, 6.4 indoors and 8.9 for outdoors. 1993, based on the epidemiological study, they gave us two values, 5 millisievert per working level month at workplaces and 4 millisievert per working level month at homes. This is the publication 65. 1 year after, ICRP developed the human respiratory tract model, dosimetric approach, and they gave us the dose conversion factor at workplace, 13.4. Although there was 1 year, but the value is quite different, 5 and 13.4. Then, in this value was calculated based on RADEP. This is Radon Dose Evaluation Program, developed by Barshall and James in 1994. After that, in 2000, based on the dosimetric approach, other researchers proposed 15 millisievert per working level month at homes with the same evaluation program. But this program, RADEP, was not available for users, normal users. Therefore, my colleague, we check the conversion factor using the general program, namely RUDEP, lung dose evaluation program. According to this analysis, we got 13.7 at work, 14.3 at homes. The results were very similar from those calculated by Radon. In 2010, based on the epidemiological study, they gave us two values. They are 9 at work and 7 at home. In this calculation, the lifetime excess absolute risk LRAR was changed from 2.8 times 10 to minus 4 to 5 times 10 to minus 4. These were calculated using ICRP 60 determinant adjusted nominal risks. 4 years after, using the ICRP publication 103, they recalculated the dose conversion factors for both workplaces and homes. As a result, there were 12 at work, 9 at homes. In the latest analysis, ICRP 137, publication 137, gave us 10 millisievert per working relevance. Yesterday, I received Professor Mehra about the difference among different dosimetric models. So there were answers. This table shows the dose conversion factors using dosimetric model. Here's the publication, ICRP publication 50 in 1987. Model type is NEA. Here is dose conversion factors I mentioned in the previous slide. Second, Anskia 2000. The same as publication 50. They gave us 5.7 indoors and outdoors, the same value. And Hare et al. In 1996, 9.6 millisievert per working relevance indoors and in mines. Postendorfer 2001, based on the ZOC model, they gave three different working scenarios. 8 at home, 11.5 at workplaces, 10.6 outdoors. At home, there was no aerosol sources. Actually, home without cigarette smoke, non-smoker's house. Next, Winkler, Hale, and Hoffman gave 7.6 millisievert per working relevance at home, based on the deterministic airway generation model. Winkler, Hale et al. In 2007, the model type deterministic airway generation model and stochastic airway generation model and human respiratory tract model, ICRP publication 66 model. They compared the difference between three models. 8.3 8.9 and 11.8. Marshall and Barchow gave us 15 millisievert per working relevance at home based on human respiratory tract model. James et al. In 2004, based on the human respiratory ICRP-66 model, they gave us 20.9 in mines and 21.1 at homes. Marshall et al. Gave us 12.5 and 12.9 in mines at homes respectively, based on the human respiratory tract ICRP-66 model. In this calculation, in mines, no hygroscopic growth was assumed. Here's a review of DCF in published data. ICRP publication 50. The reviews are available. Dosimetric models such as Hoffman et al., Jacobi and Icefield, James et al., and Harley and Pasternak. Anscare 1982, 1988, 1993. The same model was provided by NEA as ICRP publication 50. Anscare 2000 recognized that more recent calculation with new dosimetric models such as human respiratory tract model result in higher values of DCF, dose conversion factor. However, as ICRP publication 65 gave the lower values using dose conversion convention, Anscare 2000 and 2009 decided to maintain the same value as a previous report after considering it was within the range of possible dose conversion factor. Marshall and Barchow and others made a sensitivity analysis to identify those human respiratory tract model parameters that significantly affect the equivalent dose to the lungs per unit exposure to radon progeny under conditions found in houses. Anscare 1988 noted that equivalent dose may vary by a factor of 3 according to the target cells considered. Winkelhell et al. In 2007 compared the result of dose conversion factor using the human respiratory tract model, a deterministic airway generation model, and a stochastic airway generation model with the same input parameter values. They gave us the result of 8.3 to 11.8 millisievert per working relevance. Polstendorfer 2001 calculated dose conversion factors using an airway generation model developed by Zook et al. 1996. It was given as 8.0 to 11.5 millisievert per vacuum relevance. Nominal aerosol conditions in homes, workplaces, and outdoors. Regarding 4.2 to 7.1 millisievert per vacuum level mass, places one dominant aerosol source producing a high particle concentration, such as cigarette smoking or combustion aerosols by diesel engines. As you can imagine, if there are more aerosol particles, those conversion factor would decrease. See? Compare these values. Here is the normal aerosol condition. This is high aerosol conditions. James et al. In 2004 calculated those conversion factors for mines and homes. They assumed the activity size distributions given in Bayer 6 report, 1999. As a result, they got those conversion factors of 18 to 21 millisievert per working level months for mines and 16 to 21 millisievert per working level months at homes. They considered aerosol growth and presence or absence of cigarette smoke in homes. Marsh et al. In 2005 calculated dose conversion factor using the human respiratory tract model and activity size distributions for mines and homes based on measurements carried out in Europe. As a result, it was 13 millisievert per working level months in mines and homes, which were the same value. ICRP 2010 concluded dose conversion factor should be calculated using ICRP biokinetic and dosimetric models, including the human respiratory tract model and the ICRP systemic models. ICRP provided dose conversion factors for different reference conditions of dosimetric and occupational exposure, reference conditions of domestic and occupational exposure with specified equilibrium factors and aerosol characteristics. There is a main source of variability and uncertainty in calculation of dose conversion factor. I can say activity size distribution of radon progeny aerosol. Breathing rate, model used to predict aerosol deposition in the respiratory tract. Absorption of radon progeny from lung to blood. Identification of target cells and their location within bronchial and bronchiolar epithelium. Relative sensitivity of different cell types to radiation. Regional differences in the radiation sensitivity of lung. I'm explain this parameter in detail. Activity size distribution as aerosol characteristics. There are two definitions. The first one, activity median thermodynamic diameter, AMTD, it is defined as the diameter of a spherical particle that the same diffusion coefficient in air. Diffusion is the random motion of an aerosol particle caused by collisions with gas. Diffusion is the dominant mechanism of deposition in the airways for small particles of less than 0.5 micron. So this is micron, not. It can be measured by diffusion batteries using wire screen sampling. The second, activity median aerodynamic diameter. It is defined as the diameter of a unit density of the sphere that has the terminal settling velocity in air. Gravitational sedimentation is important for large particles more than 5 microns. Internal impaction is a dominant mechanism in the airways for large particles of more than 2 microns. This is also wrong. Here is micron. It can be measured by low pressure cascade impactor. There is a relationship between two diameters. AMTD equals AMTD square root 1000. Here is a shaping factor over particle density. This slide shows the classification of radon progeny aerosols with their particle size parameter, aerosol size, expression of diameter, particle density, and shaping factor. Here's unattached. It's attached. Attached fraction includes nucleation mode, accumulation mode, and cause mode. Aerosol size 0.5 to 10 in attached mode, 10 to 100 in nucleation mode, 100 to 1000 in accumulation mode, more than 1 micron in cause mode. You see, this is air activity median thermodynamic diameter, and this is the activity median aerodynamic diameter. The particle density in kilogram per cubic meter, 1000, 1400, 1400, and 1400. Shaping factor, this is 1, 1.1, 1.1, and 1.1. These are samples of particle size, activity particle size distribution of radon progeny aerosols in the environment, actual environment. Probably I show you in my last lecture. We measured particle size, activity particle size distribution in an underground mine in Japan. Here's an attached mode. Attached mode. There were 2 peaks. On the other hand, we conducted particle size distribution measurement in an actual dwelling there was no unattached peak, but we found 3 modal peaks in nucleation mode, accumulation mode, and course mode. This slide explains the behavior of radon progeny aerosols in the respiratory tract. The smallest size activity deposits efficiently by diffusion and is largely removed in the nose and mouth. The unattached fraction, about 1 nanometer particles, has limited penetration to the bronchi. If such particles increase in size due to chemical or physical processes in the air, they reach sizes around 5 nanometers. A 5 nanometer particle can effectively penetrate the nasal or oral passages but still deposit in the bronchial region. The amount of radiation that reaches the lung tissue greatly increases in the 3 to 10 nanometers. As the size continues to increase toward 100 nanometers, the effectiveness of the particle deposition decreases. In the size range above 110 nanometers, most of the deposition occurs in the deep lung, AI region. In this region of the lung, there was a very large area, so that the activity per unit surface area of the tissue is very small. For large particles above 2.5 microns, the deposition is mainly in the nose and mouth. Very few of those particles reach the critical target cells of the lung. The size of the particle containing the radioactivity in the environment is very important in determining its effectiveness in delivering dose to the tissue. This figure exemplifies the dose conversion factors expressed in millisievert per working level month as a function of particle size calculated with the human respiratory tract model or a standard worker. Unit density and unit shapes was assumed in this calculation. Here is a relationship between particle size and effective dose in millisievert per working level month. As you can see, the smaller particle give us high dose, radiation dose, but on the other hand, there are more accumulation mode particles in the environment. They gave us small radiation dose. But in the case of coarse mode particles, again, these coarse mode aerosols give higher radiation dose. Therefore, we have to calculate if you have a activity particle size distribution data, you can calculate the dose conversion factors very precisely. The sensitivity of lung dose from inhalation of radon progeny to aerosol parameter values. The variety of dose conversion factors. The dose conversion factors can be written by a function of the unattached fraction. For example, for an adult at home, the dose conversion factor can be expressed in this equation. DCF equals 11.35 plus 43 times unattached fraction. The unit is millisievert per working relevance. For an attached fraction ranging from 0.04 to 0.2, the dose conversion factor varies from 13 to 20 millisievert per working relevance. Activity site distribution of radon progeny depends on the exposure conditions, namely 10 to 21 millisievert per working relevance for homes, 11 to 26 millisievert per working relevance for workplaces, 56 millisievert per working relevance with air cleaner. Actually, unattached fraction was 0.56. As I mentioned in the previous slide, much smaller particle gave us a significant radiation dose. This is the reason why this value is higher than others. This table summarizes values of effective dose per unit exposure to radon progeny calculated with a human respiratory tract model for different exposure scenarios. Adults at home, home without cigarette smoke, non-smoker's house, around between 13 to 21. On the other hand, in smoker's house, 10 to 16 or 18, the dose conversion factor is smaller in smoker's house than in non-smoker's house. Workplace indoors, 21, 20. This is my paper. So I set the different air conditions. We measured unattached fraction and air cleaner operation. In mines, the dose conversion factor 11 to 26. Yeah. Next, breathing rate. I'll show the different breathing rates for a Caucasian population at different levels of physical activity. These data are coming from ICRP 66. They are classified with age and gender. Resting or sleeping, sitting awake, light exercise, and heavy exercise. See? The reference breathing rate ranged from 0.2 to 3 cubic meter per hour. This parameter is also dominant for dose calculation. Here's the dose conversion factors for different levels in physical activity under typical indoor exposure conditions. After considering by breathing rate also age and breathing rate, age, or any other biological parameters, the lowest dose conversion factor was given here. Adult female, 3.6. The highest dose conversion factor, in that case, 10-year-old male, 80, during the heavy exercise, 80.6. Here is the dose conversion factor for different ages under typical home exposure conditions. This is non-smoker's house and smoker's house. 3 months, 9.6. Smoker's house, 8.2. 1 year old, 11.3. 9.8 in smoker's house. 5 year, 11.3, 9.4. 10 year, 13.5 in non-smoker's house and 10.4 in smoker's house. 15 year, 11.4, 11.5 in smoker's house and 9.0 and 8.8 in smoker's house. Adult, 12.9, 12.7 in smoker's house, 9.9 and 9.2 in smoker's house. As you can see, the dose conversion factor in smoker's house is always smaller or higher than that in smoker's house. In this calculation, there are assumptions age-dependent parameters, mass of the target tissue, respiratory frequency, and tidal volume for each level of physical activity. Average time spent at each level of exercise, and lung capacities. Here's a summary of the dosimetry of radon isotopes. There are many types of dosimetric approach. The most important airborne radon progeny from the viewpoint of radiation dose to lung tissue as a consequence of inhalation are the alpha-emitting radionuclides, polonium-218, its half-life of 3.1 minutes, alpha-emitting energy 6.0 MeV, and polonium-214, its half-life is 164 microseconds. Alpha-emitting energy is 7.7 MeV. There are dominant parameters for lung dosimetry are personal or biological and environmental. As you can see, there are various dose conversion factors given with different exposure conditions. Professor Mehra, can I?
Thank you very much, sir.
Yeah.
Dear participants, if you have any question, then you may unmute yourself and ask the question. Okay, so there are no questions. Then, Tokonami sir, we can take a break of 5 to 10 minutes.
Yep. Okay. All right.
So dear participants, we will start the next lecture at 11 a.m. right after 15 minutes.
Okay.